we've done this problem two different ways. The first way that I showed you was the method that I referred to as the brute force method, which is how many reactants do you have? Oh, that's how many stoichiometry calculations you do. So we take the mass of the H2 and calculate the mass of ammonia that can be generated, and we assume that we have an excess of the other reactant, the N2. Then we flip the calculation around. We take the mass of the other reactant, the N2, and pretend we have an excess of H2. And we calculate the mass of ammonia that can be produced. Then we look at the answers and we see that, 40 grams of N2 can make 48.64 grams of ammonia. 10 grams of H2 can make 56 grams of ammonia. But we can only make 48.64 grams of ammonia because at that point we've exhausted our nitrogen, N2, and even though we have more hydrogen gas, it doesn't matter. As soon as one reactant runs out, poof, the reaction's over. So in this method, you calculate the product mass first, and from the smallest one, you identify the limiting reactant, which is N2. The other method I showed you, and this is the one that shows up in most of the chemistry textbooks that I see, is that you identify the limiting reactant first, and then from that, you calculate the mass of ammonia that can be generated. So the first thing I do is, I look at the mass of hydrogen gas, and I see that with 10.00 grams of hydrogen gas, I need 46.32 grams of nitrogen gas. Grams to moles to moles to grams between H2 and N2. But then I notice that I don't have that much nitrogen gas. I only have 40.00 grams of nitrogen gas. That means I have too much hydrogen gas. So nitrogen gas is my limiting reactant. Then I do my stoichiometry calculation going from N2 to ammonia. And I see that I can make 48.64 grams of ammonia. I don't like the second method. And that's because the chemistry textbooks that I've read that use this method, they're really careful and they only show you chemical equations that have either one or two reactants, never more than that. See, this method works fine if you only have two reactants. But what if you have more? This is the reaction that produces phosgenite. It's lead 2 oxide reacting with saline solution, ocean water, sodium chloride, carbon dioxide, and water all together to make the phosgenite. What if you have more than two reactants? What do you do? Well, this problem gets really complicated really fast using the limiting reactant comparison method. So let me just kind of go through this relatively quickly. I'm going to pick the lead 2 oxide to work with first. And what I've done is I've done 3 separate stoichiometry calculations. And it shows me the mass of sodium chloride, carbon dioxide, and water I need with 5.00 grams of lead 2 oxide. Now, look at the masses of those other reactants that I calculated. They're all less than the given masses of reactants. Since the calculated masses are all less, that means I happen to pick the limiting reactant by accident, because I have far more of the sodium chloride, carbon dioxide, and water reactants than I have of the lead 2 oxide. So then I would do my calculation based on lead 2 oxide. And I'd go from 5.00 grams of lead 2 oxide to grams of phosgenite. Change things up. Let's say I just changed the mass of the lead 2 oxide and I make it 10 grams. I do the same kind of calculation as I did before. Now look at the masses of the other reactants I need. I'm okay on carbon dioxide and water because I have more than enough carbon dioxide and water to react with 10 grams of lead 2 oxide. But I need more than 2 grams of sodium chloride, but I only have 2 grams. Okay. So now what I've done is shown that sodium chloride is the limiting reactant. And I do my calculation going from the 2.00 grams of sodium chloride to grams of phosgenite. That's the lead compound on the right-hand side of the arrow. Let's change it again. Let's say I have 50 grams of lead 2 oxide. I've just jumped right to the calculations here. And 50 grams of lead 2 oxide requires more sodium chloride, more carbon dioxide, and more water than I have. Which means the lead 2 oxide is in excess, and my limiting reactant is one of those three, but I don't know which one of those three. As it turns out, and this isn't obvious, and this is why I don't like it, the limiting reactant is the larger of the calculated masses. The limiting reactant is the 13.09 grams of sodium chloride. So just to show you, let me do a comparison to prove to you that the sodium chloride really is the limiting reactant. So take the 2 grams of sodium chloride and notice that, I need less than 2 grams of carbon dioxide, less than 2 grams of water. So the sodium chloride really is the limiting reactant. And then that's how I would do my calculation. I'd go from 2.00 grams of sodium chloride to grams of the phosgenite. There, clear, right? No, that last example I think was really complicated, but you don't see examples like that in the book. So this is how you could do it if you use the brute force method. We have 4 reactants. None of the reactants are in excess, so we do 4 different stoichiometry calculations. So we play the game with the 50.00 grams of lead 2 oxide. And we see that if we have an excess of everything else, we can make a little more than 61 grams of the phosgenite. Do it again with the 2.00 grams of sodium chloride. We see that we can make 9.33 grams of the phosgenite. Okay, now remember these 2 masses, because I got to clear some space. Then we do it again with the carbon dioxide, and we realize that we could make 12.4 grams of phosgenite. And then we do it again with the water, and we realize that we could make 30.3 grams of the phosgenite. Okay, so out of those 4 different ones, the sodium chloride produced the smallest mass of the phosgenite. So the sodium chloride is the limiting reactant, and that mass we calculated previously, that's the mass of the phosgenite. So try both methods, see which one you like better. The important thing is that you can reproduce it and that you understand it. From my own perspective, I don't care which method you use as long as you can reproduce it and understand it.